Hey everyone, Katrina here, and today we're going to be talking about exact first-order ordinary differential equations. Be sure to subscribe for more videos just like these. Okay, so this is the beginning of our ODEs series, so be sure to watch the rest of the playlist for more videos on ordinary differential equations. So we're going to be tackling a first-order differential equation, and in particular, we'll be looking at exact equations today. I'm going to take you through a couple different definitions, a three-step process on how to solve these equations, and then we're going to walk through together a step-by-step example, and by the end of this, you'll be feeling confident to tackle these equations on your exam. Okay, so let's look at this first definition right over here. So we see that, so we have some function m, which has two independent variables, x and y. And then we're adding another function n that also has these two variables, x and y, and then we can see that we're multiplying by the derivative of y with respect to x. And importantly, it equals to 0. So that's very important. So we're saying that this equation, m plus n times derivative of y with respect to x, is what we call an exact equation if there exists, so this backwards e means exists, so you can learn some new mathematical notation today. So if there exists a function f of xy whose differential equation equals to the left side of this equation below. So I have this equation below written in blue here, so you can just take a minute to note this. So we have the partial derivative of f with respect to x dx, and then we have the partial derivative of f with respect to y dy, and then that equals our exact function above, our m of xy dx, and then our n of xy dy. Okay, so that's a lot of words there and definitions. So really, what does that actually mean? So this is our formal definition, so this is good if you're going to pure math and you need some more theory about, okay, how can we actually define these? But I'm going to show you a very quick and easy definition right now. So there's two things we need, basically, if we can classify an exact equation. So thing number one is that your partial derivative of m with respect to y has to equal the partial derivative of n with respect to x. So I have it written in the short form here, and then I also have the Leibniz notation right over here, so you can see exactly the kind of slope-looking d over here represents a partial derivative sign, just so you know. So there you go. So that's the first thing. Then looking at the second criteria over here, it will be exact if your differential equation follows this form over here. So you have your m dx plus n dy, and then super importantly, it has to equal to 0. So if we have both of these things together, then we have an exact ODE. Okay, so you can use both of these definitions. I find this one is the easiest. You go through your equation, you first check if your partial derivatives are equal, and then you just ensure that your equation is in this form with 0 on one side of the equation. So our first definition over here, essentially what's happening is you're guessing some function f, and if you have this function and it can follow this form that we've outlined, then you have an exact ODE, but sometimes conceptually that can be a little bit challenging. So we're going to just stick with our definition number 2 going forward, and you can use both of these, and understanding both gives you a better holistic view of everything that's going on. So now we're going to move on to a 3-step process that you can do in order to actually solve these exact differential equations. So step 1 is we want to put our equation in the form that we saw above. So in particular, we want our form to be our, like we saw before, m of xy dx plus n of xy dy equals to 0. So sometimes we might have to rearrange our equation a little bit. Initially, when we saw over here, we had that our dy over dx was stacked here. So by having it equal to 0, you can easily rearrange your equation to achieve our desired format, which we see down here. Okay, so no need to think about this too complicatedly, if that's even a word there. We just have our mdx plus ndy equals to 0. So that is step 1. So don't be afraid or confused sometimes if you see an equation that's not already in this format. That doesn't necessarily mean that it's not an exact ODE. It just means that you might have to rearrange it in order to get to this format. So if you can't rearrange it to this format, then it cannot be an exact ODE. But if you can, then that's great. Then that means we can move on to step number 2 to continue to confirm if it's exact or not. So step 2 is, like we saw earlier, we need to verify that our partial derivative of m with respect to y equals the partial derivative of n with respect to x. Okay, so pretty much these two basically verify that we have an exact ODE, and then once we have that, then we can go ahead and kind of start to actually solve it. So in order to solve it, what we have to do is we want to integrate, this is where derivatives and integrals work together. So yeah, we want to integrate our m of x, y, dx, which you can see is our first part of our exact equation. And then we also want to integrate our second part, so our n of xy dy, which you can see is right over here. And we want to integrate both of these separately. So that's kind of like the key thing here, is that once it's in this format, instead of completing one longer, more challenging integral, we just have to integrate these separately. So essentially, by integrating these separately, it allows us to find our potential function f of x, which is our solution. Okay, so that's kind of where this ties back into our definition number 1. So we integrate both of these separately, and our final answer here is going to be the combination of both of these integrals. So we'll have the integral of our m dx, and we'll have our integral of n dy. But the main thing here to note is that you should not, so do not repeat terms. So if both of your integrals give you the output of x, for example, do not write x twice. So you only write repeated terms once, and then any other terms that are unique to both to both your m and n functions. And then lastly, our step 4, which I don't even know if it deserves its own step, is make sure you have your plus c value at the end if you have an indefinite integral. Okay? And then your final answer, this is kind of important here, your final answer will be with respect to our function f of xy, and then that will be the answer. So that will include the integral of our m, and then our integral of our n, and then our integration constant c. So this is coming back to our function. Essentially, we're finding a potential function by integrating both m and n separately, and then collecting all the terms and not repeating repeated terms. Okay, so now that you have these 3 or 4 step process here, we're going to go through an example that's going to be step by step, and we're going to see all of these processes in action. So our example today is going to cover the following function. So we have that y cos x plus 2x times e to the power of y plus sine x, I'll put this all in brackets, plus x squared e to the y minus 1 dy over dx equals to 0. So this is our differential equation. Just so you know, this dy over dx can also be written in prime notation as y prime, but for the purpose of exact equations, we do need it in Leibniz equations because, as you see before, we do take this separately and the dx separately in order to put it in that ideal form that we need. So if we follow our step-by-step process, oops, sorry about that, zoomed in a little bit too much there. So following our step number 1 is we wanted to put it in the correct form. And if you recall, our correct form is going to be our m dx plus n dy equals to 0. So all we have to do here is kind of rearrange this equation. And after rearranging it, we get that y cos x plus 2x e to the y, this is all dx, and then plus bracket sine x plus x squared e to the y minus 1 dy equals to 0. So how did I rearrange that? My step 1 here was I just, first of all, moved this over to the other side of the equation, which allowed me then to take this dx and multiply it up to this side of the equation, and then we moved the term that was on the right hand side back. So it's just a little simple algebraic manipulation over there. If you have any questions, please put them in the comments. Okay, so now that we have it in our correct form, we have to continue to verify that it's an exact ODE. So in order to verify it, we need to double check that the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So looking at our example over here, we can see that this part over here is our m function, and then this part over here is our n function. So let's go ahead and take the partial derivatives of each of these. Okay, so let's start with my, so you know that this is equals partial derivative of m, partial derivative of y, just so you see both of the notations. So pretty much what that means is we're taking the derivative with respect to y, and we're treating all other variables, which is x in this case, as constant. So since we're doing that, we're taking the derivative of y here. We see that the derivative here is simply just cos x because the derivative of y equals to 1, and cos x in this case is just considered as a constant because we're only differentiating with respect to y. Okay, and then plus, so here we have 2x times e to the y. Again, x is treated like a constant. The derivative of e to the y is simply e to the y. Okay, so we have this. And now let's check what is nx. So this is the partial derivative of n with respect to x. So now we are treating y as the constant and only differentiating with respect to x. So the derivative of sine is cos x, and right there. And then looking at this piece, we see that the derivative of x squared equals to 2x by the power rule, and then we multiply by e to the y because that's just a constant, and then the derivative of -1 equals to 0. So looking over here, we can see that the partial derivative of m with respect to y equals the partial derivative of n with respect to x. So that means we have an exact ODE because this checks out, and we were able to put it in this format right over here and have 0 on one side of our equation. So now we're going to move on to step 3, where we're actually going to go ahead and solve this. So if you recall step 3, we now have to integrate both of our sides, or both of our terms, separately. So let's start with our m function. So we're going to go ahead and integrate that one. So we're going to take now the integral of y cos x plus 2x to the power of y, And remember that we're integrating here with respect to x, because in our original function we had this as m dx. So when we integrate that, that means we're integrating with respect to x, because that is our independent variable there. So following integration rules, we can actually integrate kind of both of these terms separately because they are being separated by an addition. And since we're integrating with respect to x, that means we treat y as a constant. So it can stay right there. So the integral of cos x, so the antiderivative, that is going to be sine x, right? Because the derivative of sine is cos, so the integral of cos is sine. And then now over here, we have to figure out what is the integral. Oh, sorry, I miswrote this over here. This should be 2x e to the y. So now we need to figure out what is the integral of our 2x over here. So this is simply going to be x to the power of 2, because this is the reverse of our power rule. So if we have an aside, if we are integrating, for example, x, the integral of this is going to be x squared 1 over 2. So in this case, we already have a 2 here, so we have 2 in front, and then we have to divide this whole thing by 2 according to the integral rule. So then our 2's will cancel out, and we are simply left with x squared. And then we multiply by e to the y because y is a constant over here. And now let's do the same thing for our n function. So we have n xy. Take the integral of that. So here we have the integral of sine x plus x squared e to the y minus 1 dy. So here we're integrating with respect to y. There, so we have y sine x. And then for our next term over here, the derivative of e to the power of y, the derivative of e to the power of y and the integral of e to the power of the y stay the same. So it's just e to the y. And we multiply by x squared since we are integrating with respect to y, so we treat x as a constant there. And then the integral of -1 is simply -y. So now that we have the integral of both of these functions, we need to find our final solution. And our final answer is going to be our function f of xy. And like I mentioned before, we have to collect the terms from both the integrals, but we do not write repeated terms twice. So we see that we have a repeated term here and here. So we're going to simply write y sine x. And then we also have another repeated term here and here. So we're going to add plus x squared e to the y. And then we all have in non-repeated terms, so we're going to just add that as well, minus y. And like I said before, we have to always remember to add our integration constant because this is not a definite integral. And there you go. We have now solved our exact integral, we've now solved our exact differential equation, and you can see that this is actually a pretty simple process. You can just follow these 3 main steps, put it in the correct form, check that the partial derivatives match, and then integrate both your m and n functions, and then just gather all your terms and be sure not to write your repeated terms twice. Okay? So there you have it. We've learned how to solve a new type of differential equation. So definitely add this to your list. Be sure to subscribe for more because I'm having a full series of differential equations coming out. I'll be having other ones on separable ones, integrating factors, and also higher order. We'll be looking at methods of undetermined coefficients, variation of parameters, and so on. So definitely stay tuned. Comment any questions that you have. I'll get back to you very soon. And yeah, if you enjoyed this video, please drop a like. I'll see you next time.